All right, thanks. I am going to talk about the role of sea ice in Dansgaard-Oeschger cycles today. And this is quite a North Atlantic-centric talk. And also these atmosphere ice-ocean interactions I'm going to be talking about are sea ice, no land ice involved specifically, although it is in the freshwater. So let's see, how do I, thank you. All right, so I've gone and turned the time scale around on you. Here's 90,000 years ago up to the present. And here are the DO cycles in one of the Greenland ice cores. You can see them over here. I just wanted to put this up to point out a few things that we're going after. First is the very abrupt transitions, and then so that's a fast time scale, and then these slower millennial time scales involved, and also the magnitude of these events in some important surface climate variables. So 6 to 16 degrees Celsius of warming, 50 to 100% increase in accumulation, so in snowfall of these ice core layers. Thanks. Okay, so sea ice is a good candidate for creating the amplitude and also the abruptness of these changes. And that's because sea ice cover has this ability to undergo large, fast changes. When it changes, it also moderates the exchange of heat, momentum, moisture between the ocean and the atmosphere. So you can really you can change the surface climate and the atmospheric circulation and many things, ocean circulation, just by changing sea ice. So I'll just spend a few minutes reviewing some early results that we got. Sea ice is notoriously difficult to reconstruct, but what we can do with climate models is just test dozens of different scenarios of what sea ice might have looked like and what kind of climate response you get. So I'm just showing one example here where you have, let's say, a certain cold, if you look at the thick white line, a cold climate with a very extensive summer sea ice, very extensive winter sea ice too, and then you can push this back to where the thin line is in the North Atlantic. And we went through sort of many of these, basing them on coupled climate model runs and somewhat on what we knew from observations. But you can look at the response to this pushing back of the sea ice line. Here I'm showing surface temperature, but you can also look at snowfall that will give you some information about accumulation. You can look at atmospheric circulation patterns. And one early lesson was that winter sea ice retreat is important. And that's not really a surprise because that's where you're getting the most heat up to the atmosphere. So here is a winter retreat scenario. Here's a summer retreat scenario based on a retreat of the sea ice cover that's equivalent to the natural variability in the control runs of these simulations. So these were done with atmospheric models. And you can see about 7 to 8 degrees Celsius of annual mean warming on Greenland with this winter retreat scenario. And summer, very small signal. So the other lesson we learned, and I won't show this, but you could actually retreat more in the summer, more than we did, and you could also start warming the SSTs. If you do that, you get more warming from the summer, but you also get too much of an increase in the accumulation, so you'll get too much more snowfall, and that's not really consistent with the ice core records. Right, the other thing we learned early on was that you need to have changes in the Nordic Seas. So if you look at this black line, this is one of our stadial scenarios, extensive winter sea ice. And then this yellow line would be a retreat in the Western Atlantic, pink line retreat in the Nordic Seas. And here you see that there we go. So you really need the Nordic Seas to retreat to get a big signal up onto Greenland, a warming signal onto Greenland. I'm not saying that the Western Atlantic isn't important. This Labrador Sea area is very important, but it seems like you've somehow maxed out the Greenland warming with the Nordic Seas. And I think this could give some clues to the Heinrich events too, because you can see that you can do whatever you want over here, and Greenland probably isn't going to show a much bigger magnitude of a change. Even though you can get a longer duration for that stadial, you might not get a much deeper stadial, in a sense. So these are uncoupled experiments, which means that we just prescribed hypothetical sea ice scenarios based on some things that we thought were realistic. But it doesn't really tell us why the sea ice was changing. So if I address sort of the two hose part of this session first, you can obviously get sea ice to change by by hosing. And here I'm showing three, so these are coupled model runs now, 3 time slices. Modern, this is last glacial maximum, and obviously we would prefer to have some pre-glacial maximum climate, but that's a little harder to deal with in terms of constructing the boundary conditions for our climate model simulations. So this is an intermediate glacial case, I would say, 14K. So the colored shading is the sea ice line for the control runs in each case. And now if you look at these lines here, and it's a little hard to see, but there are a bunch of lighter colored lines and then a solid line. So these show the sea ice line after a Villinga and Wood style hosing, freshening instantaneous of the top of the upper ocean by 2 PSU, so it's a big hosing, 50 to 70 north. And the sea ice expands in all the cases. I'm showing individual winters for the decade starting 5 years after hosing, so 5 to 15 years after hosing. And there's a different number of ensemble members in each of these cases, but what you see is a different distribution after the hosing, which is expected. Also much more variability in the winter ice line in the modern case than in these two, where the individual years are tightly packed there. And also a difference in the recovery time. So Cecilia Bitz et al., they looked at this run and this run in particular. And this run recovers in a couple of decades. By 40 years after the hosing, once you've done that, it recovers. This one, even 100 years after the hosing, it hasn't quite recovered. So this map is from CC's paper. You can see a surface density, so ocean surface. And in this LGM case, you're expanding the sea ice over the densest outcroppings, which means that the system has trouble restarting North Atlantic deep water formation after you've hosed it, and it's giving you a really long recovery time. So this raises a few questions about if you're going to do the hosing. I mean, this is an unrealistically large hosing, obviously, but you still need, we need some better constraints on where the freshwater was coming from, where it was going to. We've already seen this in the talks earlier today. How much, when, with relation to the DO cycles. But also, there's the effect of the changing background climate over the 70,000 years here. So how do we put that into the picture? Because the transitions, even though the timing and duration vary, the transitions are remarkably consistent. And we know that changing the background climate matters. All right, I'll just say a few words about this. If you're not going to do hosing, you can change it just by atmospheric forcing as well. And there are ideas that the ice sheets and the size of the ice sheets can change the character of the jet and the storm tracks in a way that could make you have a more DO-friendly climate or not. I'd also like to point to there are more and more studies now showing control simulations that show spontaneous climate changes, abrupt climate changes. So this one is a poster that Hannah will be presenting later today, I think. It's in a pre-industrial control run, and she has found these abrupt transitions in Greenland temperature and sea ice that seem to have an atmospheric precursor, so something about just stochastic atmospheric variability that can force these. All right, so I'll just finish off. I'd like to mention a few things about maybe a different way of looking at the system. So looking at the question of how we can get the Nordic Seas to be ice covered, because we know that's important. The Arctic Ocean today has winter sea ice cover. The Nordic Seas has a lot of open ocean and some deep convection sites. So what we'd like to know is how we can get that Arctic sea ice into the Nordic Seas. And if we look at the Arctic today, it actually has rather a special stratification structure, vertical structure. So you have a cold, fresh surface. This Atlantic layer is made of Atlantic inflowing water that's modified as it makes its way around the Arctic basin. So the temperature maximum is actually down here, but it's also saline, so this is stably stratified. And there's a cold, salty layer here called the halocline. You can think of that as protecting the sea ice from the water below. So this nice cartoon was drawn by Alexei Numlin, who's a PhD student at the University of Bergen. And he is looking at some of these processes that help maintain this system and that will weaken or strengthen the halocline. And that would protect or threaten the sea ice cover. In a way, he's looking at modern climate, so the Arctic today. And this is an example of some of the types of experiments he can do using either idealized column models or ocean models. The reason he's going back to these types of models is because a lot of the coupled climate models have trouble representing this Atlantic layer. So they have trouble getting the subsurface warming maximum in the right place and the right strength. But here's one set of experiments where he's increased just the background river runoff to the Arctic today. And so you see in salinity, you're freshening the Arctic. In temperature, these lines represent the mixed layer. So you're thinning the mixed layer. You're actually increasing the stratification, strengthening the stratification here, making a sharper, a thinner mixed layer. You're also, it's a bit hard to see in this, but you're warming the Atlantic layer and you're moving that heat upwards. So you're bringing that heat closer to the surface, although you're strengthening the very near surface stratification. And he's testing other things as well, like changing mixing, changing Atlantic inflow properties, all these other things you can change. The reason I wanted to show this is he's found a 500 to 1,000 year time scale in this system for the halocline to adjust to whatever you do. Depending on the background climate, it varies. But that raises the possibility that you could maybe get a long adjustment time scale, so something that is equivalent to the duration or the spacing between the events from this adjustment of the column to either build up or destroy the halocline, and then fast sea ice changes that give you the transitions. And what we're seeing, I guess what you would need to do, or what we'd need to do, is to modify this for the Nordic Seas. It's a little more complicated because there are more in and out arrows than the Arctic Ocean, but that's what he's in the process of doing right now. Hansi Singh at University of Washington has created a similar system, a bit more complicated, but that shows it might be possible to get this into the Nordic Seas. And I'll just finish briefly by saying that there is some observational evidence for shifts in sea ice cover and also this subsurface warming in the Nordic Seas. So I'm not talking about over in the Labrador Seas, but up right in the Nordic Seas. This marine core of Trondheim recently, for example, that is very high resolution and it's timed, the chronology is excellent, and he can actually see at 1,500 meters depth oceanic changes that are related to brine rejection from sea ice formation, and also subsurface warming, and these are sort of matched right with the ice core record. And I think I'll end there because this is blinking at me. Thank you.
Thanks, Camille. We have time for some questions. Axel.
I totally agree that the sea ice plays a big role in amplifying the greenness signal and maybe also driving the abruptness. But do you infer also that sea ice is playing a major role in driving the large-scale global teleconnection?
Yeah, so the question was whether the sea ice, it can explain the abruptness and the magnitude maybe, but what about the larger scale global teleconnections? And I think, so the point is here that you need something over the Nordic Seas to change, but I guess what I didn't have time to get into is that's going to necessarily mean a change in a lot of other things, because if you're changing that sea ice, John Chang and Cecilia Bitz have shown that you're really going to affect, you can affect the ITCZ, you're going to affect all the way down to the South Atlantic. You're also, the overturning is just integrating that circulation across, so you are going to see a change in the overturning. And with the atmospheric teleconnections, which are fast, and that's a sensitive area too, you seem to get signals that are consistent.
Any other questions? Yeah.
How much water accumulated is produced during a hosing?
The question was how much water there was in the hosing. In the hosing experiments that I showed, those were very unrealistic. So we were freshening the top couple hundred meters of the ocean by 2 PSU. That's sort of 16 Sverdrup years instantaneous. So that's not realistic at all. We just use that because it's a typical hosing type experiment that's done to look at the sensitivity of the models. But the models react quite differently to the same hosing. That's one thing. And so we should go back to more realistic, but as we saw from some of the other talks, it's really difficult to know what to do as a realistic scenario.